Every year, only a few dozen combat machines capable of changing the course of a battle are produced worldwide. One such giant is born in the heart of the United States at the Boeing factory in Fort Worth, where every bolt, every weld seam is inspected with micron precision. Here, fuselages made from metal plates are joined into a single, strong body, and powerful T-700 engines and Hellfire missiles turn the machine into a formidable weapon. But there is one detail that only those who work behind the scenes of this production know. Watch until the end, and you will discover a secret that changes the perception of these helicopters forever. The main production facilities are located in the United States, particularly at the Boeing plants in Fort Worth, Texas, where the helicopter is manufactured using modern technologies. At these plants, the assembly of the helicopter's main components, such as the fuselage, rotors, and weapon systems, takes place. The production process includes automation to increase efficiency and accuracy, which is critically important for military equipment. An important part of the production capacity is also contracts with component suppliers. Orders for electronics, engines, control systems, and other parts come from various corners of the world. These suppliers must meet strict quality standards to ensure the reliability and combat readiness of the helicopter. In addition, the U.S. Department of Defense works closely with Boeing to control production, which allows for ensuring compliance with all specifications. This includes conducting regular inspections and tests at various stages of production to account for all potential problems. The production facilities engaged in the manufacturing of the AH-64 are also constantly improving their processes. With the introduction of new technologies and production management methods, such as lean manufacturing, the company strives to reduce costs and shorten production time without compromising quality. The main components, such as electronics, engines, navigation, and control systems, are manufactured in different countries. For example, the T700 engines used in the AH-64 are produced by General Electric in the USA. Weapon systems, such as Hellfire missile launchers, are manufactured by many defense contractors, both in the US and outside the country. The electronic system, including radar and fire control systems, is supplied from various countries, such as Israel and the United Kingdom. This allows for the integration of innovative technologies that are constantly being improved in military aviation. The delivery of components to the Boeing production facilities in Fort Worth is carried out through various logistics channels. International transport is often carried out by air and sea, depending on the urgency and volume of the cargo. Key components can be delivered by express air transport to reduce manufacturing times. Upon arrival at the Boeing plants, the components undergo additional inspection to identify possible defects and non-conformities. After the delivery of all components to the Boeing production facilities, they arrive at the huge factory territory in Fort Worth, where several hangars are organized for helicopter assembly. Here, a primary inspection of each batch of parts is carried out. Specialists carefully inspect the components to identify any defects or non-conformities with standards, which ensures a high level of quality. The production process begins with the assembly of the fuselage, which is the helicopter's foundation. In this stage of work, huge metal panels, drawn out in the form of long and wide sheets, are used. The fuselage consists of several sections that are welded together to create a single, strong body. First, the workers coordinate all requirements and drawings, focusing on the accuracy of measurements. They carefully install the fuselage base on a special platform that allows easy access to all elements. In parallel with this, engineers ensure that each element meets strict quality standards. During the fuselage assembly process, workers use a variety of tools, from electric drills to specialized welding machines. Welding takes place far from any unpredictable movements, as this is critically important. Even the slightest inaccuracy can affect the helicopter's combat stability. The flame of the welding illuminates the workspace, adding a bit of heat to the surrounding environment. After the main parts of the fuselage are joined, it is checked for leaks. This includes leak testing liquid is pumped through special pipes to ensure that the body's reliability meets the requirements. Usually, workers suspect a problem if they hear a sound similar to a whistle or a pop, which could indicate issues. When the fuselage successfully passes all tests, it is time for painting. The application of coatings is important as it prevents corrosion and increases resistance to weather conditions. After painting, the fuselage is sanded to ensure a smooth surface, and then all parts are checked again to confirm they are installed correctly. After the fuselage assembly is complete, the next stage is the installation of the electronic systems, which play a critical role in the combat effectiveness of the AH-64. After the fuselage is prepared, it is moved to a special hangar where technicians begin to carefully install various electronic components. These systems control everything from navigation to the weapon control system. During this process, specialists install elements such as radar, which provide an overview of the battlefield, as well as fire control systems. These components are particularly sensitive, so it is important to adhere to huge accuracy. Workers use various tools, such as drills and screwdrivers, as well as specialized devices for laying wires. The next step is the installation of the engines. For the AH-64, T700 engines are used, which are powerful and reliable. After the engines are delivered to the factory, technicians check them for compliance with technical specifications. During the installation process, the engines are mounted on the fuselage, and all necessary systems, such as fuel supply and cooling, are connected. This process requires great attention to detail, as the engines must be securely fixed and correctly connected. After the installation of the engines and electronics, the stage of integrating the weapon systems begins. The helicopter is equipped with various armaments, such as Hellfire missiles and an M230 machine gun. In this stage, technicians use multi-step procedures to install and calibrate the systems. Each weapon unit is equipped with electronic systems that ensure its functionality. After installation, a check for the compatibility of all components is carried out. Having completed the integration stages, the fuselage proceeds to final assembly, where various systems are connected hydraulics, as well as control mechanisms. Hydraulics provide the helicopter's mobility, and its installation is a critically important task. Technicians check all connections for tightness, as a leak of hydraulic fluid can lead to serious problems during flight. During the testing of the AH-64, a real show of technical skill takes place. Aerodynamic checks are conducted in a large open area where the helicopter takes to the air, demonstrating breathtaking maneuvers. From a height, it performs turns, hovers in the air, and makes steep descents, showing its stability and ability to react quickly to the pilot's commands. Spectators can see how the powerful engines work at maximum revs, filling the air with their roar. On the ground stand, the atmosphere is also tense. Experts closely watch every movement of the helicopter, keeping an eye on the digital indicators on the monitors. The sounds of testing the electronic system, as the helicopter actively responds to control commands, are impressively complex. When the weapon system is launched and green indicators appear on the monitors, everyone present experiences a moment of elation. It's a sign that everything is working, and the helicopter is ready for combat missions. The team of engineers is gathered on the territory. They are dressed in special equipment and focused on their work. When the entire system passes the checks, a look of satisfaction appears on the experts' faces. Each of them knows that their work is bearing fruit, and the Ready for Real Flights helicopter will become an important element of military power. These tests provide not only an adrenaline rush, but also pride in the technologies that bring it to life. Did you know that over 100 million AK-47 Patton rifles have been produced worldwide since its invention? That's an absolutely staggering number, more than all the service rifles produced by almost every other country combined. This iconic weapon, recognized globally for its ruggedness and reliability, might seem incredibly simple on the outside. But producing these millions of units requires a massive, complex industrial process involving extreme forces, surprising precision, and manufacturing secrets perfected over decades. Get ready to go behind the curtain and see exactly how an AK-47 is manufactured on a colossal industrial scale. The story of the AK-47's manufacture really begins with its design philosophy. Mikhail Kalashnikov intended it to be simple, easy to use, reliable in the worst conditions, and crucially, easy and cheap to manufacture in vast numbers. This design genius meant engineers had to figure out how to make complex parts ruggedly and quickly. The key was often using methods that didn't require extreme precision machining on every single component, focusing tight tolerances only where absolutely necessary for function. This is a core secret behind its mass production success. One of the most visually impressive and important manufacturing processes for the AK-47 is IAE's stamping. Unlike many other rifles that use heavier, milled receivers, the AK-47 often uses a receiver made from sheet metal. Picture huge rolls of steel sheet being fed into massive, powerful presses. These presses stamp out the receiver's shape in stages, bending, forming, and punching the metal with tons of force. This high-speed stamping process is incredibly efficient, churning out receivers faster and cheaper than almost any other method. It's a core reason millions could be made. While the receiver is often stamped, many critical components that face extreme stress and heat, like the barrel, the bolt carrier, and the bolt itself, are made by forging. This involves heating steel billets, solid blocks of high-strength steel, to incredible temperatures until they're red-hot and malleable. Then, giant forging presses or hammers pound or squeeze these glowing pieces into complex shapes. The force involved is immense, thousands of tons, reshaping the metal's internal grain structure to make the part incredibly strong and durable. This is where raw power meets shaping, creating components tough enough to withstand the explosive forces of firing. Even though simplicity was key, certain areas of the AK-47 require remarkable machining crude precision for reliable function. The bolt, which locks into the receiver, and the chamber end of the barrel, where the cartridge sits, must meet tight tolerances. These parts are finished on computer numerical control machines that use hardened cutting tools to shape the tough steel with incredible accuracy. While not every surface needs mirror-like precision, the critical interfaces that ensure safe and reliable firing are machined to exact specifications, often measured in thousandths of an inch. Bringing all these parts together involves other vital metalworking processes. Welding is used to join stamped receiver components and attach parts like the gas block to the barrel. Industrial welding robots, or skilled human welders, create strong, reliable joints. Heat treatment is also critical. Components like the bolt and bolt carrier undergo processes like hardening and tempering, heating and cooling cycles that change the steel's properties, making them incredibly resistant to wear and impact, vital for the rifle's legendary durability in harsh conditions. Once all the metal components are fabricated and treated, they often go through finishing. This includes processes like parkerizing, bluing, or applying polymer coatings. These aren't just for looks. They're crucial for protecting the metal from corrosion, especially important for a rifle designed to operate in wet, muddy, or humid environments. Furniture, the stock, handguard, and pistol grip, is often made on separate lines from wood or polymer, and then added to the metal assembly. The final stage is Cockpit assembly. While many steps are automated, putting together the hundreds of components of an AK-47 often still involves significant human skill on assembly lines. Workers fit parts together, install springs, pins, and levers, turning a pile of components into a functional rifle. Each rifle is inspected visually and functionally as it comes off the line. The true test of an AK-47's manufacturing is its legendary reliability, and this is verified through rigorous quality control and testing. Rifles are subjected to dimensional checks and material tests. Crucially, they undergo proof testing, firing rounds with an intentionally heavier charge than standard to ensure the weapon can safely withstand extreme pressure. Some are even subjected to brutal environmental tests, dunked in mud, buried in sand, submerged in water, and then expected to fire immediately. This extreme testing validates the ruggedness built into the manufacturing process. Producing millions of AK-47s requires vast factory complexes, intricate logistics, and a highly skilled workforce. It's a fascinating intersection of design philosophy, focused on simplicity, and industrial processes capable of achieving rugged reliability on an unprecedented scale. While the rifle itself is often seen as a symbol of conflict, its manufacturing process is undeniably a powerful example of mass production engineering and durability-focused fabrication. So, the next time you see an image of that instantly recognizable silhouette, remember the unseen journey it took. From raw steel and wood, through giant stamping presses, powerful forging hammers, precise machining centers, intense heat treatments, and rigorous testing, it's a product of a massive, impressive industrial process. It's a fascinating look into the power and precision that builds one of the world's most widespread tools. What part of manufacturing an AK-47 surprised you the most? Let us know in the comments. Every year, over 3 million hand grenades are produced worldwide, and each one goes through dozens of stages. From melting metal to precisely dosing explosives with an error of less than 1/1000th of a gram. There's no room for error here. Temperature, pressure, humidity, everything is under control. But what exactly happens behind the walls of classified workshops? How is simple metal turned into a deadly tool with a mathematically precise geometry of destruction? If you watch this video until the end, you'll learn about technologies that keep even national aeronautics and space administration engineers on edge. Despite strict restrictions and high danger, every step of production takes place in specialized conditions, with the use of advanced technologies that ensure the safety of workers and the high quality of the final product. First, in the production of explosive grenades, components are used, each of which has a clearly defined function and industrial standards. Although the exact recipes of the explosive substances themselves, such as trinitrotoluene, penthrite, or RDX, are secret due to their extremely dangerous nature, it is known that these substances are made from a mixture of chemical reagents that go through several phases of purification and stabilization. The production of these components takes place in controlled reactors with strict adherence to temperature and pressure regimes, where even a small error can lead to an accident. Metal blanks undergo primary processing. They are cleaned, brought to the required temperature, and if necessary, alloying additives are added to achieve the specified characteristics of impact toughness and hardness. The next key step is the forming of the grenade shell itself, which is done either by high-pressure die casting or cold stamping. In die casting, the metal is brought to a liquid state and poured into a complex steel mold, several to 5 feet long, under enormous pressure, up to 20,000 psi. These molds already account for the necessary relief details and seating for the fuse and explosive charge. An alternative method is cold forming, where pieces of sheet or bar metal weighing 1 or 2 pounds are pressed in dies with powerful mechanical presses. The pressure can reach 30,000 psi. This creates a capsule of precise geometry, with walls averaging 1/10 of an inch thick, but with options for reinforcement in critical zones. One of the most important elements is the final surface treatment of the body. The grenade body undergoes milling, grinding, and also mandatory creation of a relief texture. This is either scoring or a solid textured grid, which together with internal concentric grooves, ensures predictable fragmentation into hundreds of sharp fragments with a diameter from 1/16 to 1/8 of an inch. It is this microstructure of the shell that sharply increases the effectiveness of destruction within a radius of 40 or 50 feet. After mechanical processing, each body is chemically and technologically strengthened. Heat treatment is carried out to increase impact resistance, and it is also galvanized or painted for corrosion protection. In large workshops, each part comes off an automated line, and operators monitor the process's accuracy through integrated sensors for measuring thickness, geometry, and distances between the scoring ribs. All this complex logistics, control regime, and special materials are aimed at only one thing, so that when the grenade is used, the body fragments uniformly, creating the maximum number of deadly fragments of a given size and shape. This is a modern approach to designing explosive devices, where even the surface structure has a critical significance for completing a combat mission and surviving in extreme conditions. The explosive substance, which determines the force of the explosion, is dosed in powder or granular form with an accuracy of fractions of a gram. This material is placed in the inner chamber of the body, where a special charge is made. The filling process is carried out in automated workshops under the close supervision of surveillance cameras with remote control. Around the explosive charge, the main initiation mechanism is placed, which consists of a detonator and a fuse. These mechanisms are high-tech devices that are activated when a lever is pressed or after a delay during the grenade's flight. The current level of automation in grenade production not only allows for increasing the speed of unit output, but also significantly reduces the risks of accidents. Security services constantly monitor temperatures, vibrations, and humidity levels in the premises. Both classic metal parts and the latest composite materials are used to create the internal mechanisms, which reduce the product's weight without sacrificing strength. One of the most complex stages is the integration of all components into a single structure. This resembles the high precision of a medical operation. Complex parts are assembled on assembly lines with an accuracy of thousandths of an inch. All operations take place in special rooms without access for unauthorized persons, using specialized tools. After assembly, each explosive device undergoes multi-stage testing. The tests include checking the body seal, functional testing of the detonation mechanisms, and evaluating the uniformity and reaction speed of the initiator. The production cycle of one unit of an explosive device can last from several hours to several days, depending on the model's complexity, the degree of workshop automation, and safety requirements. These products undergo several stages of strict inspection and quality control, which includes the use of X-ray scanners to check the internal structure, as well as conducting simulated impact tests under the control of artificial intelligence. Engineers involved in the development and production of this product are in constant close cooperation with military structures, receiving clear technical specifications and updated requirements dictated by changes in tactics and combat technologies. The body materials, explosive mixtures, and fuse designs are periodically updated to ensure maximum effectiveness and storage safety. The production of explosive devices is a combination of chemistry, metallurgy, mechanics, and electronics with the highest level of control over all processes. The continuous development of technology leads to the use of increasingly sophisticated computer simulation systems that allow for predicting the behavior of combat grenades in various use scenarios. The power of such devices is measured in pounds of TNT equivalent, where universal hand grenades can correspond to an explosion of about 0.5 pounds of TNT. The dimensions usually do not exceed 5 inches in length and about 3 inches in diameter, which makes the grenade compact and easy to carry in combat conditions. As a result of the production of these swift and versatile combat tools, every step is a balance of speed, accuracy, and safety, where the quality of the product and the lives of soldiers in battle depend on the operator's professionalism. This process is not just mechanics and chemistry, it is a complex discipline that requires deep knowledge and attention to every detail. The production of hand grenades is an important component of the defense industry, with continuous improvement of technologies and control, which repeatedly sets new standards of quality and safety. It is thanks to this technical level that being true to one's task ensuring maximum effectiveness on the battlefield becomes possible. But what is the most important thing in the production and use of hand grenades? That's right, avoiding accidental detonation. It is known that the modern evolution of grenades is associated with the introduction of insensitive munitions that are more resistant to mechanical impacts and temperature fluctuations, which reduces accidents and losses from unauthorized explosions. Over the past 20 years, the share of such impact-resistant products in new Western contracts has exceeded 50%, and the number of incidents with accidental detonation has been reduced by more than 70%. An impressive figure, isn't it? The number of grenades used in military operations and training varies depending on the intensity of combat actions. For example, during active phases of major armed conflicts, the consumption of hand grenades can reach thousands of units per day for one large formation, while for training and range firing, from 1 to 3 million grenades are used globally per year. A significant portion of the finished products is exported, and in some years, the share of exports can exceed 60% of the total output. Every year, over 6 million tons of styrofoam are produced worldwide. But what if we told you that this lightweight material hides technologies that seem like science fiction? It all starts with oil, goes through boiling reactors, multi-ton extruders, and gas magic to become perfectly porous blocks. And what's most surprising, all of this is increasingly being created from trash. How exactly does plastic get a second life? And why might styrofoam be banned in some countries in just a few years? Watch until the end, because the finale will surprise you. The production of styrofoam is a complex multi-stage process that begins with a raw material, most often polystyrene. Polystyrene granules are the primary raw material for the production of styrofoam and other plastic products, and their production begins with a chemical process called the polymerization of styrene. First, the monomer styrene is obtained, a colorless liquid that is a product of oil refining or chemical synthesis from petroleum fractions. In special reactors, under controlled temperature, pressure, and the presence of catalysts, styrene monomers bind to each other, forming long polymer chains, polystyrene. This process occurs in several stages, where parameter control ensures the required degree of polymerization and final physical properties, such as strength, flexibility, and thermal conductivity. The substance transforms from a liquid state into a viscous plastic material. Next, the polystyrene is cooled and formed into large briquettes or granules. For granulation, the molten polystyrene is passed through special extruders, which extrude the plastic mass through numerous thin holes, similar to how dough comes out of a pastry bag. When the thin strands come out, they are quickly cooled in water baths or air streams, and, with the help of cutting equipment, are cut into small granules of a standard size. The most acceptable are grains from 0.04 to 0.2 of an inch. In recent years, a significant portion of the produced styrofoam contains secondary polystyrene. In the United States, this figure reaches 25% of the total volume, which helps to reduce the environmental impact of the industry. The introduction of modern technologies allows for a reduction in the emission of volatile organic compounds, including pentane, by about 30% compared to previous decades. The granules have a uniform shape and size, which facilitates further transportation, storage, and dosing in the styrofoam production cycle. They are supplied to factories in large bags or silos, from where they are sent to the drying stage as needed to remove moisture. The news is that modern manufacturers are increasingly implementing technologies for recycling used and spent plastic products back into polystyrene granules, thereby reducing the environmental impact and increasing economic efficiency. This cyclical process allows not only to obtain new granules, but also to reduce energy consumption and harmful emissions, which is important for the sustainable development of the industry. The production of styrofoam in the US and worldwide is steadily growing due to increasing demand in the construction, packaging, and automotive sectors. Annually, global production capacities for expanded polystyrene exceed several million tons. The demand for thermal insulation materials is growing at an average of 4 to 6% annually, which stimulates investment in new technologies and line modernization. Polystyrene granules are delivered to the styrofoam manufacturing plant, usually in specialized containers. The most common method is large industrial bags that hold from 1,000 to 3,000 pounds of granules at once. Such bags are loaded onto trucks or containers for transport. Sometimes the granules are transported in sealed containers, silos, or large plastic containers that protect them from moisture, dust, and foreign impurities. Delivery is handled with particular care in regions with high humidity, as even a small amount of moisture in the granules will negatively affect the quality of the styrofoam. At ports or logistics centers, the granules are unloaded using forklifts and transferred directly into the factory's silos. From there, they are fed through pneumatic transport systems or conveyors to the drying and preparation zones for further processing. The entire delivery chain is a carefully organized process that minimizes the contact of granules with the environment and contamination. The good news is that thanks to modern packaging and transportation methods, most factories receive already dry, clean granules, ready for the uninterrupted start of the styrofoam production line. This significantly improves the quality of the final product and reduces production losses. The energy required to produce 1 cubic foot of styrofoam is approximately 1 kilowatt-hour or less, which has been subject to optimization in recent years, taking into account environmental standards. When polystyrene granules enter special heating machines, one of the most important stages of styrofoam production begins: the partial melting of the raw material and the formation of a porous structure. These machines are usually extruders, large cylindrical devices several feet long, in which the granules are heated to 320 degrees Fahrenheit. Inside the cylinder, a screw rotates, a spiral blade that slowly pulls the granules forward, simultaneously mixing and heating them to the technological temperature. As the granules pass through the extruder, the heat combines with mechanical friction, causing the polystyrene to transition from a solid to a viscous, almost liquid state. This process is called plasticization or melting. At this stage, the granules do not completely turn into liquid, but acquire a thick, cream-like consistency, which allows them to easily pass through the screw and forming holes. It is to this molten mass that a blowing agent is introduced, a special gaseous substance, most often pentane, a representative of environmentally safe volatile organic compounds. The blowing agent is added in a controlled amount so that it begins to evaporate in this hot environment, forming gas bubbles that become cavities inside the material. In the thick cream, thousands of tiny gas bubbles gradually appear, evenly distributed throughout the mass. These gas pores are the future structure of Styrofoam, providing its lightness and thermal insulation properties. The process happens very quickly, and the temperature along with the pressure in the extruder are controlled by computer systems that maintain optimal conditions for pore formation. Next, this gas-saturated, but still viscous mass passes through a mold or extruder plates with holes of a certain size. There it is expanded into sheets or blocks of the required thickness. Immediately after exiting the mold, the material is cooled by a water or air cooling system, which fixes the pore structure, making the material hard, but at the same time very light and resilient. Simultaneously, the material is subjected to a cooling system to stabilize its structure. Rapid cooling fixes the formed pores so that the Styrofoam does not collapse. As a result, a lightweight, porous material with a density of approximately 3.5 pounds per cubic foot is obtained, depending on the type of Styrofoam and the customer's requirements. Next, the Styrofoam is cut into sheets or blocks of specified sizes, often 4 feet by 8 feet, which is the standard in construction. These sheets undergo quality control, including checking for compressive strength, water absorption, and thermal insulation characteristics. The total weight of such sheets depends on the density used, but usually ranges from 5 to 25 pounds. The product is packaged and labeled for transport. It is expected that by 2030, market growth and technological progress will make Styrofoam an even more environmentally friendly and versatile material. Every year, over 2 billion tons of asphalt are produced worldwide. But there's a place where even road pavement is an engineering art. Imagine, in the middle of a desert, under a 120-degree sun, asphalt is born that doesn't melt, doesn't crack, and even reflects light. How do oil residues from a tanker turn into a super-modified mixture that withstands sandstorms? And what do the RTA laboratories in Dubai hide? If you watch until the end, you'll find out what they never tell you in promotional brochures. It all begins on the waves of the Persian Gulf, where giant tankers slowly cut through the water's surface, carrying millions of barrels of black gold, crude oil. It travels from Iraq, Saudi Arabia, Kuwait, countries where sand and fire have intertwined in an eternal dance of energy. When a tanker slowly docks at one of the UAE ports, for example, at Jebel Ali, one of the largest man-made ports in the world, an act begins where technology and people work as a single organism. Oil, having just completed a transcontinental journey, is pumped into huge tanks, like into concrete hearts. These tanks, hidden in the industrial landscape, are the beginning of the transformation, where raw material becomes the essence of civilization. Next, it travels underground, in pipelines, like arteries leading to oil refineries. In Jebel Ali or Abu Dhabi, it is met by reactors, distillers, chrome columns, and heating furnaces. There, it is heated to a temperature of over 660 degrees Fahrenheit to separate it into fractions. Light components, gasoline, diesel, kerosene, evaporate first. The heaviest residues, which do not evaporate even at high temperatures, are exactly what will become the basis for asphalt. This residue is called heavy fuel oil or vacuum residue. It is fed into a vacuum column, where the pressure is reduced to a minimum, allowing for the separation of even more light fractions without thermal destruction of the heavy molecules. What remains after vacuum distillation is bitumen, a black, viscous substance that is the basis for asphalt. Bitumen itself is too thick and rigid for use in road construction, especially in desert conditions where temperatures can reach 120 degrees. Therefore, it is modified. In special reactors, it is mixed with polymer additives, plasticizers, stabilizers, and sometimes even rubber crumb. This process is called bitumen modification. The result is a material that has high elasticity, resistance to ultraviolet light, does not soften in the sun, and does not crack at night when the temperature drops sharply. In Dubai, polymer-modified bitumen is mainly used, which meets the standards of the RTA, the Emirates Road Agency. When bitumen completes its transformation in specialized reactors, acquiring elasticity, heat resistance, and the ability to withstand the infernal desert sun, a new stage of its journey begins: delivery to asphalt mixing plants. The modified bitumen from the reactor enters heat-insulated tanks that maintain its temperature at approximately 350 degrees Fahrenheit. In a liquid state, it maintains its homogeneity and readiness for mixing with mineral components. Then it is pumped by high-pressure pumps into sealed pipelines leading to the plant, or, if the plant is located at a distance, it is poured into tank trucks with special thermal containers. Such tankers are built with a double steel body, with an insulating layer that prevents the bitumen from cooling during transport. The road to the plant is like the roots of a city's circulatory system, where every drop matters. The drivers of such bitumen trucks undergo special training. They must maintain a stable speed, avoid sharp braking, and monitor temperature sensors in real time. If the temperature starts to drop, heating is activated so that the mixture does not lose its properties. At the plant, for example at DXB Asphalt Factory in Dubai Industrial City, the tank truck enters a receiving complex where it is connected to the unloading system via reinforced thermal hoses. At this moment, the bitumen is hot, thick, with a characteristic smell reminiscent of a mixture of rubber and metal. It is pumped into intermediate mixing tanks where it waits for dosing. From this moment, it becomes part of the recipe, in a formula where the weight, viscosity, and temperature of each component determine the durability of the future road surface. One of the largest is the DXB Asphalt Factory in Dubai Industrial City. There, bitumen is heated to 320 degrees Fahrenheit and mixed with mineral aggregates: gabbro, basalt, quartz, sand. Gabbro is a dark volcanic rock mined in the mountains of Fujairah. It has high density and strength, which makes it an ideal aggregate for road pavement. The stone is crushed into fractions smaller than an inch, sifted through vibrating screens, dried in drum dryers, and fed into a mixer. In the mixer, bitumen and aggregates are combined into a hot mass called hot mix asphalt. The temperature of the mixture is 320 degrees Fahrenheit. It must be homogeneous, without lumps, with a precise ratio of components. For this, automated dosing systems are used, which control the weight of each ingredient. After mixing, the asphalt is fed into silos, where it is stored for no more than 6 hours so as not to lose its properties. From there, it is loaded into dump trucks with thermal insulation, which deliver the material to construction sites. On site, the asphalt is distributed over the surface using asphalt pavers, machines that evenly spread the mixture on the roadbed. Then it is compacted with rollers, first vibrating, then static. In the desert, it is important to achieve maximum density to prevent the penetration of sand and water. Therefore, compaction is carried out in several passes, and the asphalt temperature during paving must be at least 250 degrees Fahrenheit. If it drops, the mixture loses its plasticity, and the road will quickly deteriorate. A feature of Dubai's highways is that they have a multi-layer structure. The lower layer is coarse-grained asphalt, which provides load-bearing capacity. The middle layer is made of modified bitumen, which acts as a shock absorber. The top layer is a thin layer with a polymer coating, which provides grip with the wheels and resistance to abrasion. In some cases, light-reflecting minerals are added to reduce surface heating. In the desert, it is important to consider not only temperature, but also dust, wind, and humidity fluctuations. Therefore, asphalt plants in Dubai are equipped with air filtration systems, and the mixtures themselves are tested for resistance to abrasive wear, thermal expansion, and even sandstorms. In the RTA laboratories, Each batch of asphalt is checked for viscosity, density, water absorption, and thermal stability. If the indicators do not meet the standards, the material is returned for reprocessing. This process, from a tanker of oil to a finished road, takes several days but requires dozens of control stages. And it is thanks to this that Dubai's highways withstand the load of thousands of cars every day, do not melt under the sun, and do not crack at night. Asphalt here is not just a black mass, but an engineering system that combines oil, stone, polymers, and desert endurance. Over 1 million tons of asphalt are produced annually in Dubai, and this figure is growing along with the expansion of infrastructure. The DXB asphalt factory alone has a capacity of 240 tons per hour, which allows for supplying large projects without interruptions. For comparison, an average plant in Europe produces about 150 tons per hour. Interestingly, asphalt is the most recycled material in the US, and over 99% of old pavement is returned to production. In Dubai, recycling is also being actively implemented, especially during the reconstruction of old roads in industrial areas. And from which country are you watching us? Every single day, at the Lockheed Martin factory in Fort Worth, Texas, fighter jets roll off the production line, ready to dominate the skies. This is where the legendary F-16 Fighting Falcon is assembled, each one a true engineering marvel. In just 52 days, hundreds of specialists, robotic systems, and thousands of components come together to create a combat machine capable of reaching speeds of 1,500 miles per hour. How is this steel predator built? I visited the factory and saw it all with my own eyes. Ready to dive into the heart of aircraft manufacturing? Buckle up, we are taking off. At the massive Lockheed Martin factory in Fort Worth, Texas, the day begins with the roar of machinery. Gets the adrenaline pumping, right? My heart is racing. Here, in the heart of aerospace engineering, one of the most famous fighter jets in the world, the F-16 Fighting Falcon, is brought to life. But the process of building each F-16 begins long before the first part arrives at the factory. Engineers at Lockheed Martin start by working with 3D modeling systems using CATIA V5 and Siemens NX software. A digital twin of the aircraft is created to test virtual aerodynamics, simulate material strength, and optimize the placement of cables, pipelines, and electronic systems. After that, supercomputers run numerous simulations to predict how the F-16 will perform at different speeds, in combat maneuvers, or under extreme temperatures. To test the strength of the structure, prototypes of key components, such as the wings, nose section, and tail, are built and subjected to rigorous lab tests. They undergo vibration-resistant simulations to mimic turbulence, as well as extreme temperature exposure, heating up to 302 degrees and cooling down to -76 degrees Fahrenheit. And let's not forget impact resistance tests, like simulating a bird strike at 559 miles per hour. You love crash tests too, right? It is thrilling. Meanwhile, a separate team works on the cockpit. Test pilots evaluate the ergonomics of the instruments, the positioning of the HUD display, and the ease of control. As for the materials, supply issues are never a concern. Lockheed Martin signs contracts 2 to 3 years in advance. The standard material set includes aluminum and titanium alloys from Alcoa and Timet, which form the fuselage structure, composite materials from Toray and Hexil, used for wings, fairings, and radar-absorbing elements. Aerospace electronic systems, including radars, avionics, and targeting systems, are provided by Northrop Grumman and Raytheon. In the morning, the factory floor at Lockheed Martin has a quiet but focused atmosphere. This is not just manufacturing. This is where fighter jets that will rule the skies are born. Workers are at their stations. Some are prepping riveting guns, others are reviewing blueprints, while some are operating laser measuring systems. Today, another F-16 Fighting Falcon is being assembled, and everything must be flawless. As you might have guessed, the factory follows a modular approach. Instead of building an entire jet in one place, it is assembled in sections before being joined together. In one of the workshops, the aluminum cockpit frame is already complete. Nearby tables hold avionics instruments, HUD displays, and computer system modules. Workers in white gloves carefully install them into compartments. The ejection seat mount is fitted, and a 12mm thick bulletproof canopy glass is installed, capable of withstanding a 13mm bullet impact. 12.5 miles of wiring are laid out, connecting sensors, displays, and control systems. Meanwhile, the central fuselage section is being assembled, the area that houses the fuel tanks, landing gear, and wing mounting points. A large aluminum frame is secured with 40,000 rivets installed by automated riveting robots. Fuel tanks with a total capacity of 845 gallons are integrated into the structure. The landing gear, capable of handling loads up to 44,000 pounds, is installed and tested. Workers meticulously check the tanks for leaks by filling them with a special gas and inspecting for any seepage. In the adjacent workshop, the tail section takes shape. It is welded together using titanium and composite panels, with an engine mount already in place, designed to withstand temperatures exceeding 2,192 degrees Fahrenheit. The elevator and rudder are then installed, followed by a check on the emergency braking mechanism. A specialized team handles this section since the tail not only controls flight, but also maintains the jet's overall balance. The wings are assembled in a dedicated section. Hydraulic mechanisms for controlling flaps and ailerons are installed, along with hardpoints for weapons. The composite wing surfaces undergo ultrasonic testing for defects. If even one layer of carbon fiber is improperly placed, the wing could deform under combat stress, so there is zero tolerance for errors. Once all modules pass rigorous inspections, they are transported to the final assembly line. The final assembly line is a massive hangar stretching 437 yards long, where hundreds of specialists work in precise coordination. Everything follows a strict schedule. Any delay in one step can impact the entire process. The central fuselage is lifted by a specialized crane and aligned using lasers. First, the cockpit is attached, followed by the tail section. Engineers use high-strength titanium bolts capable of withstanding loads of approximately 88,180 pounds. Once the primary structure is complete, it is time to attach the wings, which are secured with reinforced titanium joints to ensure structural rigidity. Engineers meticulously check the alignment angles to ensure the error margin does not exceed allowable limits. After assembling the airframe, one of the most critical moments arrives: the installation of the jet engine. It is transported in a specialized container and lifted into the tail section using a hydraulic hoist. Technicians carefully connect all systems: fuel lines, hydraulic and electrical cables, and the afterburner system that enables supersonic flight. Once installed, a dry test run is conducted to verify its operation without fuel ignition. The onboard computer, pilot displays, weapons control systems, and the ANAPG-83 radar, capable of detecting targets at a range of 100 miles, are then integrated. Before the first flight, the F-16 receives anti-corrosion treatment, paint, and stealth coating. As a kid, my best friend was obsessed with origami. She was into everything from Eastern culture, so origami never stood a chance of being ignored. Me? I was terrible at it. My fine motor skills were not exactly top-notch, so while she was crafting intricate dragons and delicate flowers, I was busy making paper planes of all sizes and launching them from my window into the backyard. Could I have imagined back then that I would one day step into the legendary Lockheed Martin factory and witness the birth of an F-16 with my own eyes? Absolutely not. Before an F-16 takes to the skies, it must undergo a series of ground tests. Every flight system, electronics, fuel supply, and hydraulics is tested on the ground first. The engine is warmed up to operational temperature, and the exhaust system and airflow temperature in the ducts are inspected. Special attention is given to the ACES-2 ejection seat and emergency systems that might be needed in a crisis. Once all ground systems pass, the pilot receives clearance for the first flight. Communication with ground controllers and engineers is checked in real time. The jet slowly rolls toward the runway, then accelerates to around 3,000 yards per hour for an optimal takeoff. After liftoff, the landing gear retracts smoothly, Everything is functioning perfectly. At an altitude of around 3,300 yards, the pilot executes the first maneuvers, testing aerodynamics, elevator, aileron, and flap responses at different speeds. The F-16 is then pushed past Mach 1 to test the afterburner system. This phase measures aerodynamic stress, identifying any defects at high speeds. G-force tests follow, as the pilot executes precise maneuvers to ensure stability under varying attack angles and velocities. After completing initial flight tests, the pilot begins the descent. At 3,000 yards, the landing gear deploys, and the pilot prepares for touchdown. The effectiveness of brakes and the auto-stabilization system is evaluated. The moment the F-16 touches the ground, it decelerates quickly. Engineers conduct final inspections of electronics, fuel systems, and structural integrity. Data is then analyzed, and if everything checks out, the F-16 is officially cleared for duty. This is one of the most expensive and complex machines ever built by humankind. Constructing it costs more than $3 billion and takes over 7 years to complete. It can dive to depths of more than 3,000 feet, remain submerged for months without surfacing, and launch missiles capable of altering the course of war. But how exactly is a nuclear submarine, an engineering masterpiece that remains nearly invisible even to the most advanced radars, built? Right now, you are about to witness this incredible process. A nuclear submarine is a highly sophisticated engineering marvel, and its creation begins long before the first sheet of metal ever touches the manufacturing tools. The initial designs are developed using advanced computer modeling software. At this stage, several critical parameters are considered, including hull dimensions and shape, power systems, weaponry, and noise reduction technologies. The length can range from 300 to 550 feet, directly impacting the submarine's diving depth based on its class. The most advanced submarines can descend to depths of 2,000 or even 2,500 feet, while some experimental models can go beyond 3,000 feet. Based on these initial designs, physical models of the submarine are constructed and tested in water tunnels. This allows engineers to analyze how the hull shape affects maneuverability, water resistance, and noise levels. Meanwhile, computer simulations help predict the submarine's behavior underwater at different speeds and during various maneuvers. Once all simulations confirm the calculations, the blueprints are sent to production. This is where theory turns into practice. Building nuclear submarines requires special materials capable of withstanding extreme pressure at great depths while providing corrosion resistance. Typically, high-grade steel or titanium alloys are used. Steel is more cost-effective and easier to manufacture, as it can endure high pressure and impacts. Titanium, on the other hand, offers superior strength, corrosion resistance, and non-magnetic properties, which reduce the risk of detection. However, titanium is more challenging to process and weld, as its melting point is significantly higher, approximately 3,034 degrees Fahrenheit compared to steel's 2,500 degrees Fahrenheit. Before construction begins, all metal sheets undergo heat treatment, which involves heating, cooling, and applying special anti-corrosion coatings. The hull of a modern submarine is assembled from modular sections, simplifying the construction process. Metal sheets are cut with massive laser and plasma cutters, ensuring precision down to the millimeter. Each sheet is then shaped using hydraulic presses to achieve the desired curvature. Some parts of the hull feature spherical or cylindrical structures. The sections are assembled separately. These are massive rings, or compartments, that will be joined in the final stage. This modular approach allows different sections of the submarine to be worked on simultaneously, accelerating the overall construction timeline. Once all components are ready, the most critical phase begins: welding the hull. Welded seams must be exceptionally strong, as even a microscopic crack could lead to catastrophe at great depths. To meet all safety standards, automated electron beam welding is used, producing perfectly uniform seams. Additionally, every weld is inspected using ultrasonic scanners and X-rays. Most nuclear submarines feature a double hull design. The strong inner hull withstands deep sea pressure, while the outer hull provides a streamlined shape, improving hydrodynamics and reducing detectability. Ballast tanks are often located between these hulls, allowing for buoyancy control. To keep the submarine as stealthy as possible, anti-sonar coatings are applied. These include noise-dampening polymer tiles that absorb sound waves, microporous composite materials that minimize the submarine's acoustic signature, and noise-reducing coatings for the propellers and power systems. Once all sections are ready, they are connected. Gigantic cranes transport the compartments into specialized docks, where they are bolted and welded together. The completed hull is then tested for air tightness by filling it with compressed air and checking for leaks. A structural integrity test is also conducted in a hydrostatic pressure chamber, simulating real deep-sea conditions. Once the submarine's hull is assembled and its strength verified, it is time to install its most crucial component, the nuclear reactor. This is the heart of the submarine, allowing it to stay submerged for months, or in some cases, even years. A nuclear reactor is more than just a machine. It is an entire energy system consisting of various auxiliary components that occupy a significant portion of the submarine. Modern nuclear submarines use reactors that function by heating water to generate steam. The nuclear fuel, typically enriched uranium-235 or uranium-238, is placed inside the reactor's core. As nuclear reactions occur, heat is produced, which then heats water in a closed-loop system. The resulting steam drives turbines that generate electricity and power the propeller. The reactor is transported in protective containers and installed using cranes through a designated hatch on the upper part of the hull. It is placed within a specialized compartment in the submarine's core, surrounded by radiation-blocking materials. This compartment is also equipped with emergency cooling systems and reinforced safety barriers. The reactor is mounted on a shock-absorbing platform that minimizes vibrations and impacts during submarine movement. Next, heat exchangers and steam generators are installed to ensure efficient coolant circulation, followed by the installation of turbines and electric generators, critical components for the submarine's overall operation. Finally, the compartment is sealed with multi-layered lead and composite panels to minimize radiation exposure to the crew. To ensure functionality, an initial test ignition of the reactor is performed. During this test, power levels are gradually increased, radiation levels in all compartments are measured, and cooling systems are tested under maximum loads. With the reactor in place, the submarine is still far from operational. At this point, it consists of empty corridors and compartments, so the next step involves installing control systems, life support mechanisms, weaponry, and crew quarters. Sonar systems are mounted in the bow and along the hull, enabling the detection of enemy vessels and underwater terrain mapping. The onboard computer system and automated combat control stations are integrated, ensuring precise maneuvering capabilities. Weapon systems are also installed. Torpedo tubes are positioned at the front, equipped with automated reload mechanisms for rapid firing. Strategic submarines are fitted with missile launch silos located in the central hull. Each silo is equipped with hydraulic locks and pressure control systems, allowing for missile launches at extreme depths. Considering that the crew can remain submerged for months without surfacing, nuclear submarines must be self-sufficient. They are equipped with oxygen generators, carbon dioxide removal systems, heating and ventilation mechanisms, and water reserves. Ever seen those tiny capsule hotels? Well, submarines have something very similar: sleeping capsules. They also feature dining areas stocked with provisions and a command center filled with control panels, maps, and communication devices. After the living quarters are fully equipped, the submarine is almost ready for deployment. But the most thrilling phase remains: a series of rigorous tests to prove that it can withstand immense pressure, stay undetectable, maneuver in extreme conditions, and perform combat missions. These tests can last anywhere from 6 months to 2 years, and include both factory trials and combat training for the crew. The submarine undergoes another airtightness test, followed by assessments of its electrical and navigation systems, and a final reactor ignition. For the first time, the submarine leaves the shipyard and enters open waters. Stabilizers, hydraulic cylinders, and steering mechanisms are tested. Sharp turns, dives, emergency maneuvers, and maximum speed tests, typically 25 or 35 knots, are performed. The submarine then submerges to periscope depth, about 65 feet, to evaluate stability. At greater depths, ballast tanks are tested under load, and the submarine is gradually lowered to its maximum allowable depth, usually around 2,000 feet, depending on its class. Reactor performance under maximum load is also assessed. Once the submarine has proven its seaworthiness, combat systems are tested. Initial shots are fired using training torpedoes without warheads. Strategic submarines conduct the launch of a single ballistic missile, typically following a launch-dive-airburst trajectory. Tactical submarines perform test launches of Tomahawk missiles or similar weapons. The submarine also enters an area with hydroacoustic sensors, where specialists measure noise levels at various speeds and evaluate the effectiveness of its sound-absorbing rubber coating. Finally, the submarine undergoes a simulated combat mission, during which the crew must demonstrate full operational readiness.